Welcome everyone, I'm Andrea Ziani and today I'm going to present you our paper TempCLR, Reconstructing Ends via Time-Coherent Contrastive Learning. The task that this project tackles is 3D hand reconstruction, hence training a neural network such that it reconstructs a 3D hand mesh from a single color image. However, this is a particularly challenging task because of the occlusion that arises during hand and object interaction or self-occlusion during normal conversation. In particular, most methods in the hand reconstruction literature struggle with heavy occlusion due to a lack of 3D label data. Improving the hand reconstruction of such methods in this scenario would require a collection of labels in unconstrained environments with different lighting conditions, occlusions, grasp, and objects. But is there a way to improve hand reconstruction under heavy occlusion without additional label data? In this project, we try to give an answer to this question. For instance, analyzing this sequence, one can notice that the pose, the global orientation, and the translation of the hand are quasi-static. However, images in the video change from frame to frame, causing a state-of-the-art method to fail. Can we leverage the temporal information in this video to produce better hand reconstruction? Concretely, we show how to leverage unlabeled videos of hand interacting with objects to improve 3D hand reconstruction in the challenging heavy occlusion setting. The 3D hand reconstruction of TempCLR are temporally smooth and robust to heavy occlusion in comparison to previous state-of-the-art methods. Our approach consists of two stages: a time-contrastive pre-training stage and a supervised fine-tuning stage. In the first stage, we aim to learn an encoder that attracts the embeddings of frames close in time, as they likely to contain similar hand poses. The cosine similarity-based loss encourages embedding of similar neighboring frames to be mutually attracted, while those of dissimilar frames in the same sequence are kept far apart. In this way, the latent representation of frames representing similar hand poses, here shown on the right, are closer in comparison with the latent representation of another pre-trained encoder, here shown on the left. Next, we perform a supervised fine-tuning on the 3D hand reconstruction task. In this stage, the pre-trained encoder and the hand decoder are trained with full supervision to predict mano pose and shape parameters, and the weak perspective camera parameters. Our novel contributions are twofold: a data augmentation strategy and a probabilistic pair sampling technique. Geometric data augmentation, such as image rotation, scale, and translation, are extensively used in contrastive training. For example, TempCLR proposes to attract the latent representation of two different augmentations of the same image. However, since two different geometric augmentations of the same image represent different hand poses, Spoor et al. Propose an equivariant contrastive formulation to overcome this issue. In a temporal setting, however, geometric augmentation can break motion cues between consecutive frames, affecting the final performance. To address this problem, we apply the same geometric transformation across different frames of the same sequence. On the other hand, appearance transformations are applied independently to each frame. This allows us to achieve invariance to appearance transformation while preserving the motion cues of the sequence. Also, a vanilla time contrastive training repels any non-neighboring frame in a sequence. In a hand-grasping object scenario, however, several consecutive frames usually represent a similar hand pose, and a naive pair selection may not be beneficial. We use a sampling strategy to account for this problem. In details, given an arbitrary frame xi in a video, we define a window around the frame, here dots shown in gray. From this window, we sample positive pairs with a probability that monotonically decreases with the distance from xi. Similarly, we sample negative pairs lying outside the window with a probability directly proportional to the distance from xi. Following this strategy, the contrastive training objective focuses more on attracting temporally nearby frames and repelling distant frames. In this way, the importance that is given to the frames with uncertain similarity to xi is reduced. Here we show our results. We evaluate our method on in-the-lab and in-the-wild datasets, composed of hand-grasping object and hand-solo sequences. By comparing the reconstruction of TempCLR with the state-of-the-art method, one can see that in this sequence, TempCLR is more robust to heavy occlusion caused by the interaction with the object. In this sequence, TempCLR produces smoother hand reconstruction even when sudden changes in hand poses are present. Our method outperforms the state-of-the-art across all the hand reconstruction metrics on HO3D, and is even on par with a specialized architecture trained with additional weak supervision. Our method also outperforms previous state-of-the-art contrastive learning approaches on freehand. To better understand our method, here we provide ablation analysis. We investigate the impact of our pre-training objective with respect to different amount of human annotated data and in the wild unlabeled data. For these plots, the baseline uses an ImageNet pre-train encoder, while for TempCLR, we apply time contrastive pre-training either using HO3D only or HO3D plus 100 days of hands. The fine-tuning and the evaluation are conducted on HO3D. We can see that TempCLR consistently improves hand reconstruction by leveraging additional unlabeled data, and the use of additional in the wild unlabeled data further improves our performance. To validate our key contributions, a temporal consistent augmentation strategy and a probabilistic sampling technique, we show TempCLR performance when either of the two is removed. The table shows that the most significant improvement in hand pose estimation coming from the augmentation strategy. Contrary, the sampling strategy contributes more to the temporal stability. We measure the temporal stability in terms of acceleration error, measuring the difference in acceleration between the 3D ground truth and the predictions. The combination of the two strategies leads to the best performance. This confirms our intuition that time contrastive learning is more beneficial when considering the changes of the hand pose in time. In addition, we investigate the effect of different sampling strategies. We compare linear sampling, exponential sampling, and sampling using the absolute value of the hyperbolic tangent function. We see that the linear sampling leads to the best performance. We now show the limitation of our approach. Our method struggles to predict correct hand poses when the hand is not clearly visible for an entire sequence. If the hand is occluded since the beginning of a sequence, it is hard for the method to recover. It produces coherent hand poses through time, but they are all correlated with the wrong initial prediction. Our method could lead to unstable hand reconstruction if uncontrollable geometric transformation, such as zooming changes, happen during the sequence. This problem arises since our time-coherent augmentation strategy does not account for this unexpected geometric transformation happening over time. These sudden changes could in principle be modeled by applying independent geometric transformation per frame. However, this degrades the overall hand reconstruction performance. We have therefore decided to favor the hand reconstruction performance over the corner cases of unexpected geometric variation. To summarize our presentation, we introduced TempCLR, a novel contrastive learning approach for 3D hand reconstruction. Our method leverages time-coherent augmentation and a probabilistic sampling strategy to capture long-range dependencies. We show that by leveraging unlabeled video data, TempCLR outperforms existing methods across different metrics and datasets. We provide empirical evidence to show that our method leads to smoother hand reconstruction over time. Thank you for your attention and check out our project page for more details.